नहमदुहु व नसल्ली अला रसूलिहिल करीम अम्मा बa'du फ़अऊज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम. Dear viewers, this tutorial is about phase lock loops and their role in demodulation of FM modulated signals. Phase lock loop is a circuit that synchronizes a locally generated signal to an input signal in frequency as well as in phase. In this synchronized or the so-called locked state, the phase error between the local signal and the input signal is zero or it is very small. If a phase error builds up, the feedback control mechanism retracts the local signal as to minimize the phase error with the input signal. The phase of the local signal is locked to the phase of the input signal, hence the name phase lock loop. A PLL circuit consists of three basic components: a phase comparator, also known as phase detector, a loop filter, and a voltage control oscillator, and it's more commonly known by its acronym VCO. We will discuss these components in more detail after a couple of slides. PLLs were popularized by television and were responsible for keeping heads on top of the screen and feet on bottom. Otherwise, there would have been a vertically scrolling picture. To enhance the quality of the TV receiver, the local oscillator responsible for vertical scan was phase locked to the sync pulses by so-called flywheel synchronizers implemented by phase lock loops. The term flywheel originates from the high inertia of the synchronizer, enabling it to move through periods of high noise and weak input signal without losing synchronization. Phase lock loops are used in television, cell phones, GPS, satellite receivers, etc. PLL is used for carrier recovery, for FM demodulation, frequency synthesis, generating higher frequencies from smaller stable crystal frequencies, recovery of clock signal from sequential digital data, and clock distribution circuits. To understand FM demodulation, assume an FM modulator signal UFD is applied at input. The sinusoid carrier frequency is Fc and its phase phi-t is proportional to the message signal MFT integrated. The frequency sensitivity Kf determines the depth of the FM modulation. VCO output Vyt is another sinusoid frequency Fc and phase phi-Vt proportional to integral of VCO input Vt. VCO is just another FM modulator. At the receiver side, phase comparator output is the phase error between the input FM signal UFT and VCO output signal Vyt. The low filter has impulse response GFT, its input is phase error phi et, and output is Vt. We will later see that under low conditions Vt is proportional to the message signal MFT. The FM modulated signal ut, a sinusoid with its argument given 2 pi fct plus 2 pi kf integral mt dt. We define the instantaneous frequency of a sinusoid as time derivative of its angle part, and omega is the instantaneous frequency of incoming FM signal in radians per second or Fi Hz, calculated as time derivative of argument of the sine function in ut, and we get, if we define the frequency deviation delta f as difference between the carrier frequency Fc and the instantaneous frequency Fi, rearranging we get, and so the frequency deviation is proportional to the message signal MFT. Frequency modulation is varying the frequency of the carrier signal around a center frequency proportional to the message signal, and hence we have correct representation for FM modulator signal MFT. Let us discuss the VCO. By definition, it is a circuit which has its frequency proportional to the applied input voltage Vt. In absence of Vt, VCO runs at its free run frequency Fc. KV is the VCO deviation constant in units of Hz per volt. For FM signal, its value is in range of 100,000 Hz per volt. VCO output given is as a sinusoid with phase angle proportional to the integral of VCO input Vt. The second component of PLL is phase comparator. It compares the phases of incoming FM signal UT and VCO output YVT by employing a mixer. A device that mathematically multiplies the two signals according to trigonometric product formula. We obtain two sinusoids with sum and difference angles. The sum angle sinusoid has 4 pi fct term. Therefore, its spectrum is centered at 2fc. A low pass filter after mixer will stop high frequency term, giving a sine function of phase difference. Under low conditions, this phase difference is small. Using the limit x approaches 0, sin x over x equals 1, the phase comparator output is proportional to the phase difference, from now onwards known as phase error. Now let us see how the FM demodulation takes place. So phi et is the phase difference between the phases of FM input and VCO output, which after substituting the phi Vt with its value, the integrated VCO on input Vt and taking the Laplace transform we get, and where we use the fact that integration is replaced by a pole at 0 in Laplace transform. Noting that the VCO input Vs is the product of loop filter input and its impulse response in frequency domain, Vs is replaced with phi Es times Gs. We get the phi s as function of phi Es, and since Fourier transform is Laplace transform with s replaced with j2 pi f, and noting that VCO deviation constant kV is a large number with value of Gs close to unity in passband, the fraction term is much greater than unity within the signal bandwidth, and therefore phi s can be approximated as phi es times 2 pi kV Gs over s. Now again using the factored product phi es and Gs gives the VCO input Vs, and then rearranging to write Vs as function of phi s, and noting the derivative in time domain as a multiplication by s in Laplace domain, the inverse Laplace transform gives Vt proportional to the derivative of phi t, and since phi t originally was phase of the incoming FM modulated carrier and that phase was proportional to the integral of the modulated signal mft, we obtain Vt, which is given in terms of mt. Kf and Kv both are constants, therefore Vt is proportional to mft, which is our desired demodulated signal.